So now let's do a 4-bar linkage example using our fundamental relative motion examples. So here it will be a long process, but I want to get us used to using these relative motion equations just in case we get a simpler question. But in the next video we will solve this question in a very quick way using equations provided under the mechanical engineering section. So here it's the long approach using the fundamental relative motion equations provided in the dynamics section on page 115. So we're told we have a 4-bar linkage shown. Crank 2 is driven by angular velocity omega 2 of 45 radian per second clockwise. So this is going to be our crank 2. It's denoted by the number 2, meaning it's this link. Crank 2, this is the crank, the link 2. So omega 2 is 45 radians per second that's applied at this link. So we're told the angular velocity radian per second of link 3 is most nearly what? This is link 3. The number 3 is the link number. And what we want to find is what angular velocity omega 3 is this? At these specific angles, right? At these specific angles, at this condition, when we have that 45 radian per second applied at crank 2. So essentially this is crank 2 or link 2. This is link 3, right? This is what link? This is link 4 and this is link 1. And I believe this is how it's denoted in the handbook under 4-bar linkages in the FE handbook. And we're told this is A, B, C, D. So we know A is the links of the links. A is 4 inches, B is 10 inches, C is 12 inches, D is 10 inches. And the nodes, as denoted in the handbook, this is O2. It's a pin, it's fixed. This is A, this is B, and this is O4. And we know this bottom link, link 1, is always fixed. That does not move, right? So that's special about a 4-bar linkage. And let's actually solve this. So we're going to use, again, the long approach. And in the next video, we will use just the equations provided in the handbook under mechanical engineering. So let's use the long approach, relative motion. So the first step is we will say, let me actually write down what we want to find. What we're given is obviously shown in the figure, but what we want to find is essentially our omega 3, right? That's the end goal. And this is the question, and it's in radians per second. So the angular velocity in link 3. So our solution, we will apply relative motion equations. Let me actually write down where these are at. So the relative motion equations are in the handbook. And it's a handy section on page. It's going to be page 115. So it gives us the position vector equations, the velocity and acceleration. And it breaks it down into the respective, let's say we have a velocity with respect to a certain position, we break that down into omega times r. So in this case, let's first begin from this point. So what the approach here is, we will begin at O2, then move to A, then end at B. Because this is what we're concerned with, is finding omega 3. We're not going to go all the way down here. So we're going to focus, essentially go from A, O2, A, B, and that's what we will do. And I think also we will consider O4, sorry. So we will actually look at all of these. We'll consider the whole process. But we will start at O2 and move this way. Then from A we will move this way. Then from B we will move this way. So let's first focus on this link and what happens there. And the first thing we will look at is, how does the velocity at A, VA, change? So we know VA, the velocity that occurs at A, is going to occur something like that, in that direction. This is going clockwise, so it will cause this node to move that way in that direction. And we know it's always perpendicular to the link, right? To the link here, in this case, this link, link 2. So it's always at a 90 degree or perpendicular. That's the velocity at A. And let's apply the relative motion equation for that. We're going to say that for step 1, that the velocity at A is going to equal to the VO2, the velocity at O2, plus the velocity at A, so this is A with respect to O2. Picture this as saying we're sitting at O2 and looking at A. So it's the velocity at A with respect to O2. This is where we're sitting. So we have that, and if we actually break this down further, once again, it's the velocity at A is going to be the velocity of O2 plus the velocity at A with respect to O2. So that's the equation. And again, that's in the handbook, and that's broken down for relative motion. So we have that. Now let's break this down further. VA equals to what? What's VO2? At this pin, we're not moving, right? This will not go to the left, right, up, or down. It's fixed. So at that pin, the velocity at O2 is actually 0. So this is 0. So we have 0 plus, what's VA with respect to O2? So VA with respect to O2 can be broken down into omega crossed with the position vector. Specifically, the position vector RAO2. The position vector of A with respect to O2. So the way we will break this down, it's going to be omega 2 crossed with what? It's a cross product with RA with respect to O2. So that is always the case when we're looking at this term. It's always omega time crossed with the position vector, RAO2 in this case. So it's going to be omega 2 because we're focusing on this link, right? Let me denote something on the side. If we have a bar, let's say the velocity is here, it's perpendicular. The velocity with respect to this point is always R cross omega, or omega crossed R. Omega times R. And I believe that's in the handbook somewhere as well. So in this case, we will have to consider the position vector and omega as well. And we apply the cross product. So now let's break this down further. We're going to say the velocity at A equals to omega 2 is going to be clockwise. We're going to assume, let me write this, our directions. And we're going to say clockwise is going to be negative and counterclockwise is positive. So clockwise is negative. In this case, this is clockwise, so it's negative 45 degrees. So this will be negative 45 degrees. And now since we're doing a cross product, we have to assign a unit vector direction, or a direction. So if we break this down into the unit vector directions, so to simplify this, I'll just draw something like this. Let's say this is the I hat direction, this is the J hat direction. In the Y it's J, in the X it's I. So I'll just denote this as X. J, think of it as in the Y direction. And for the K, it's going to be into and out the page. So coming towards us and into the page. So this is the K hat direction. So for this case, we will say we're looking this way, right? So K is coming towards us or into the page, and J is going to be the Y. This is essentially the 2D plane. This is the Y is J and X is I. So that's important to understand with respect to the cross product. We always have to assign those directions. So omega 2 is going to be in the K direction, right? It's going to be in the K direction, and that's going to be negative because we're going to say clockwise it's negative. It's going clockwise, so it's negative 45 in the K hat direction. And we're going to say this is crossed with the position vector. We start at O and go to A, so it's a position vector. We will have respective I and J components. So we start at O, and what I'm going to do is say we're going to go negative I hat, so negative in the I, and we're going to go, we're ending at A, we go up in the J, right? So it's positive in the J. Again, we start at O and end at A. It's the position vector. We start at O, end at A. So to find that, what I did is, we know this is 120 degrees. This angle we can find, right? All you do is take 180 minus 120 degrees, and it gives us 60 degrees. So to get this I component, again, it's negative. What do? We just do negative that length of the link, which is going to be 4 inches. The length of this bar is A, right? It's 4 inches. So we do negative 4 inches cosine of 60. And that's how we get the I component. Again, it's negative because we go to the left. It's negative. Keep that negative. And the J component, all we simply do is take the hypotenuse, which is the A value. It's 4 inches. So it's 4 inches sine of 60. And it's positive. So let me write that down here. This position vector, the I component is negative, right? It's negative 4 inches cosine of 60 degrees. Then we do in the I hat direction, it's negative. Then we do plus 4 sine of 60 degrees in the J hat direction. So that's the position vector RA with respect to O. Again, we start at O, we go negative in the I, and we know that negative I is negative. The A value of 4 inches, the hypotenuse is 4 inches, cosine of 60, and we go up in the J, so it's positive 4 sine of 60 degrees. That's how we can get that. So we have that, then we can simply apply the cross product. So VA equals to the cross product. Let me denote the positive sign convention for the cross product. So we know that this will be our positive. So if we do I cross with J, we get positive K. But if we do K cross with J, we get negative I, right? Because this is the positive. This way is positive. So in this case, we have negative 45 in the K crossed with I. So what we do is K crossed with I will be positive, right? So we carry the negative still. So a negative times a positive is still a negative. So we do that and we get Ki, we multiply this value times this value, we get the J value, right? And we get, for that J, we should get, sorry, this is a negative times a negative, it's a positive. So we do K crossed with I is positive J, right? Negative times a negative is a positive, and a positive times a positive is a positive. So we get positive 90 in the J. Then we do the negative 45 in the K hat times the 4 sine 60 degrees in the J hat. So we have K hat times J hat gives us a negative because we're going this way, right? So it's a negative times a negative, it gives us another positive. So it's positive 155.9 in the I hat because we did K times J. K times J gives us I, right? So that's that, and all of this will have units of meter per second. So we have that. That's step number 1. Let's keep going. Step number 2. We're not even close yet, but we will move to now this, what happens at this velocity, the velocity at B. So we know the velocity at B is going to do something like this. It's always perpendicular to the link, so it will do something like that. It's perpendicular to the link at 90 degrees. So the velocity at B, we write the same, essentially the same relative motion equation. We're going to say the velocity at B equals to which velocity? We will look at the velocity at A, right? Velocity at A plus the velocity of B with respect to A. So the velocity at B equals, what's the velocity at A? We just found that, right? So we just do the 90 in the J hat plus the 155.9 in the I hat. So we actually just find that. And we do plus the velocity at B with respect to A is going to be the omega 3 crossed with the position vector RB with respect to A. So let's break this down further. We're going to say the velocity at B equals to the 90 in the J plus the 155.9 in the I. Then we do plus, let's assign the direction. Omega 3 is always in the K, and we're going to assume it's going to be clockwise. So it's negative, right? Clockwise is negative K hat. So let me actually erase this and put negative in front. So it's negative omega 3 in the K hat direction. Crossed, this is a cross product. The position vector RBA. So let's do that, RBA. So we start where? We start here and go to the right in the I and go up in the J. So we go to the right in the I hat, so it's positive. So this distance is I, it's positive I, and we go up in the J, so it's positive J. Positive J, J hat. So all we do for the I is take the length of B, the hypotenuse, which is 10 inches, 10 inches times the cosine of 47.28, and the J component is positive as well, so we take the hypotenuse of 10 inches, sine of 47.28. So let's do that. We will simply write that as 10 inches cosine of 47.28 degrees. Then we do, that's in the I hat, right? It's positive. Then we do 10 sine of 47.28 degrees, and that's in the J hat. So this is in the J, and they're both positive. So at the end, what we will have to do is apply the cross product here and break this right side down. So I'm gonna just bring this down. So the velocity at B equals to 90 J plus 155.9 in the I, and we're gonna say it's going to, we will apply the cross product now for this portion. So I'll just write down what I got. You can double check, but it's a cross product. Just do the cross product using your sign convention or whatever way you choose to do it. And what I got is omega 3. So let me actually put the numbers on the outside. It's going to be 6.78 omega 3. That's in the J. It makes sense. We take K times I should give us this in the J, and then we do K times J, it gives us the I component, right? So we do plus the 7.35 in the omega 3 in the I. In the I. So let me keep the I like that, and we have, actually that's a J, and let me put an I here. So that's what you do when you break down that cross product here. And this, again, I just brought down. So we have that, and that's going to be an equation. We'll say this is equation 1. So I'm going to label that equation 1, and we'll come back to it. So the last step, the last major step, is to again apply relative motion equation, and now we're looking at the last link. So we're gonna look, how does the velocity at B change now? How does this velocity change with respect to this position, right? Now we're sitting here, right, with respect to 04. So let's erase this. We know the velocity will do something like this. With respect to here, it will do something like this, right? Velocity at B. This will assuming that goes clockwise, and it's 90 degree, right? So that's what we're going to do, focusing on this link 4. So let's do that. So the velocity at B is going to equal to velocity 04 at the pin, right? It's going to be what we have here, velocity 04 plus what? Plus the velocity at B with respect to 04. We're looking at velocity at B sitting at 04. So breaking this down further, the velocity at B, this velocity at 04 is just 0, right? Because once again, it's a pin. This has no velocity. So it's 0. So this is 0 plus the velocity at B with respect to 04, that will be negative. So we're going to say it's negative omega 4, and we're going to say crossed with the position vector RB 04. So breaking this down, we're going to say the velocity at B equals to the negative omega 4 is in the K, right? So it's negative omega 4 in the K hat direction. Then we do crossed the RB with respect to 04. It's a position vector. And what you can do is just use this angle. And we know we start at 04 and go to B, right? So you can do negative in the I. We go negative this way. So it's negative I hat. Then what you can do is go up in the J, right? Go up all the way up here in the J. So it's positive J hat. And you just take the C value, the hypotenuse of 12 inches, times cosine of 64.63. So it's negative though. For the J, you just take the C value, the hypotenuse of 12 inches, times sine of 64.63. That's the position vector. So what we will write here, we will say it's going to be the negative 12 times cosine of 64.63 degrees in the I. Then we have positive 12 times sine of 64.63 degrees in the J. And close that. So now you just apply the cross product and we can simplify this. The velocity at B equals to 5.14, and that's going to be times omega 4 in what direction? In the J hat. So I did K times I gives us J, and that's what we get. Then you do K times J and we get plus 10.84 omega 4 in the I hat. And I'm going to call this equation 2. So we have two major equations that help us relate. We're going to essentially relate them to each other in terms of systems of equations. It's going to be specifically equation 1 and equation 2, right? Because we will have this equation, and we will derive a system of equations. So we're going to equate equation 1 to equation 2. So I write this here. So this step is to equate equation 1 to equation 2. So the way this would look, we just take the equation 1 here and equal it to this equation. That's all that means. So we just take the first equation, equation 1. So it's 90 in the J plus the 155.9 in the I. Then we do minus 6.78 omega 3 in the J hat. Then we do plus 7.35 omega 3, and that one is in the I hat, right? This equals to equation 2, which is just this equation, right? So we do 5.14 omega 4 in the J hat. Then we do plus 10.84 omega 4 in the I hat. Again, equation 1 equals to equation 2, and equation 1 is this one, right? That's equation 1 equals to equation 2. And now this is the special trick we have to use. What we're going to do is extract all of the I components and J components. So let's take out the I components only. So I'll denote this down here. Let's take out the I components only. Where's all the I components? It's this component. That's J, that's J. This is I. Let's take this out. And let's take this out. Only those components. So we take 155.9 in the I then we do plus 7.35 omega 3 in the I. Everything should be I. Then we do equals to, respect the equal sign, keep this equal sign, is 10.84 omega 4 in the I. So that was the I components. Now let's do the same and take out all the J components. So for the J components, which ones do we have? Let me use red. It's this component. This component is J, right? And this component. Basically what's left over. This one, right? So let's do that. We will take 90 in the J minus 6.78 in the J, and that will be 6.78. So that red doesn't help, but it's going to be this one, right? We take that out and this one, all the J's. So it's omega 3 in the J equals to this one. So respect that equal sign is 5.14 omega 4 in the J. So we have that, and now what I'm gonna do is actually just erase the J and I components. So simply what we can do is just erase these, and we see something that we can work with, right? It's going to be a system of equation. So it's a 2 by 2. So we have the columns match, which is nice. This is just values. We have these. So we have the two equations, two unknowns, and we can solve the system of equations. So you can do the substitution method or whatever method you choose to do. And the way I did this was further reduce this to the following. So I just, on the left side, I kept just the values. So I just kept the 155.9 and equals to 10.84 omega 4, and I move this to this side, so it's going to be minus 7.35 omega 3. So that was the first equation, and the bottom equation is the J one. So I just kept the 90. So let me keep that. So I just kept the 90 here equals to this one, so 5.14, and we do the omega 4 plus, because I move this is a negative, you move it to this side, it becomes positive 6.78 omega 3. So next, what you can do is use your TI-36X Pro that's allowable on the FE exam. So what you can do is go to second, system solve, 2 by 2 linear, so it's a 2 by 2, and plug in what we have. What I'm gonna say is that this component, let me denote these here, this is my X, this is my Y, this is my X, this is my Y. So when I solve for this, the X is omega 4 and the Y is omega 3. So solving for this, I'll just plug in the X. What's in front of the X is 10.84. So 10.84. Then we do minus, so that's a negative symbol, 7.35. Enter. And equals to 155.9, right? 155.9. We have that. Then we do the bottom equation. So we do 5.14, that's the X value. And we do plus 6.78, so plus 6.78. And that equals to 90. So if you just plug all of that, it solves it for you real quick. So the X value is 15.44. That's actually omega 4. So omega 4 is 15.44 radian per second, but that's not what we actually want, but we solve for that in the meantime. but omega 3 is going to be our y value, right? This one is the y. So for the y value, you just press down and it's 1.57. 1.57 radian per second. And that will be our answer for this one. And in this case, it should be B. That's all for this. Thank you.